Software testing. Testing is intended to show that a program does what is intended to do and to discover program defects before it is put into use. When you test software, you execute a program using artificial data. You check the results of the test run for errors, anomalies, or information about the program's non-functional attributes. The testing process has two distinct goals. One, to demonstrate to the developer and the customer that the software meets its requirements. For custom software, this means that there should be at least one test for every requirement in the requirements document. For generic software products, it means that there should be tests for all of the system features plus combination of these features that will be incorporated in the product release. Number 2, to discover situations in which the behavior of the software is incorrect, undesirable, or does not conform to its specification. There are consequences of software defects. Defect testing is concerned with rooting out undesirable system behavior such as system crashes, unwanted interactions with other systems, incorrect computations, and data corruption. The first goal leads to validation testing, where you expect the system to perform correctly using a given set of test cases that reflects the system's expected use. The second goal leads to defect testing, where the test cases are designed to expose defects. The test cases in defect testing can be deliberately obscure and need not reflect how the system is normally used. Of course, there is no defined boundary between these two approaches to testing. During validation testing, you will find defects in the system. During defect testing, some of the tests will show that the program meets its requirements. The diagram shown in the figure may help to explain the differences between validation testing and defect testing. Think of the system being tested as a black box. The system accepts inputs from some input set I and generates the output in an output set O. Some of the outputs will be erroneous. These are the outputs in set OE that are generated by the system in response to input in the set IE. The priority in the defect testing is to find those inputs in the set IE because these reveals problem with the system. Validation testing involves testing with the correct inputs that are outside IE. These simulate the system to generate the expected correct outputs. Testing cannot demonstrate that the software is free of defects or that it will behave as specified in every circumstance. It is always possible that a test that you have overlooked could discover further problems with the system. As Edgar Jagestra, an early contributor to the development of software engineering, eloquently stated, testing can only show that presence of errors, not their absence. Testing is part of a broader process of software verification and validation. V&V. Verification and validation are not the same thing, although they are often confused. Barry Boehm, a pioneer of software engineering, succinctly expressed the difference between them. Validation. Are we building the right product? Verification. Are we building the product right? Verification and validation processes are concerned with checking that software being developed meets its specification and delivers the functionality expected by the people paying for the software. These checking processes start as soon as requirements become available and continue through all stages of the development processes. The aim of the verification is to check that the software meets its stated functional and non-functional requirements. Validation, however, is a more general process. The aim of validation is to ensure that the software meets the customer's expectation. It goes beyond simple checking conformance with the specification to demonstrating that the software does what the customer expects it to do. Validation is essential because requirements specification do not always reflect the real wishes or needs of the system customers and users. The ultimate goal of verification and validation processes is to establish confidence that the software system is fit for purpose. This means that the system must be good enough for its intended use. The level of required confidence depends on the system's purpose, the expectations of the system users, and the current marketing environment for the system. Number one, system purpose. The more critical the software, the more important that it is reliable. For example, the level of confidence required for software used to control a safety critical system is much higher than that required for a prototype that has been developed to demonstrate new product ideas. Number two, user expectations. Because of their experiences with buggy, unreliable software, many users have low expectations of software quality. They are not surprised when their software fails. When a new system is installed, users may tolerate failure because the benefits of use outweigh the cost of failure's recovery. In these situations, you may not need to devote as much time to testing the software. However, as software matures, users expect it to become more reliable, so more thorough testing of later versions may be required. Number three, marketing environment. When a system is marketed, the sellers of the system must take into account competing products, the price that customers are willing to pay for a system, and the required schedule for delivering that system. In a competitive environment, a software company may decide to release a program before it has been fully tested and debugged because they want to be the first into the market. If a software product is very cheap, users may be willing to tolerate a lower level of reliability. As well as software testing, the verification and validation processes may involve software inspections and reviews. Inspections and reviews analyze and check the system requirements, design model, the program source code, and even proposed system tests. There are so-called static V&V techniques in which you don't need to execute the software to verify it. As shown in the figure, the software inspections and the testing support V&V at different stages in the software process. The arrows indicate the stages in the process where the technique may be used. Inspections most focus on the source code of a system, but any readable representation of the software, such as its requirements or a design model, can be inspected. When you inspect a system, you use knowledge of the system, its application domain, and the programming or modeling language to discover errors. There are three advantages of software inspection over testing. Number one, during testing, errors can mask, hide other errors. When an error leads to unexpected outputs, you can never be sure if later output anomalies are due to a new error or are side effects of the original error. Because inspection is a static process, you don't have to be concerned with the interactions between errors. Consequently, a single inspection session can discover many errors in a system. Number two, incomplete versions of a system can be inspected without additional cost. If a program is incomplete, then you need to develop specialized test harness to test the parts that are available. This obviously adds to the system development cost. Number three, as well as searching for program defects, an inspection can also consider broader quality attributes of a program, such as compliance with standards, portability, and maintainability. You can look for inefficiencies, inappropriate algorithms, and poor programming style that could make the system difficult to maintain and update. Program inspections are an old idea, and there have been several studies and experiments that have demonstrated that inspections are more effective for defect recovery than program testing. Fogan reported that more than 60% of the errors in a program can be detected using informal program inspections. In the clean room process, it is claimed that more than 90% of defects can be discovered in program inspections. However, inspection cannot replace software testing. Inspections are not good for discovering defects that arise because of unexpected interactions between different parts of a program, timing problems, or problems with system performance. Furthermore, especially in small companies or development groups, it can be difficult and expensive to put together a separate inspection team, as all potential members of the team may also be software developers. As shown in the figure, an abstract model of the traditional testing process as used in plan-driven development. Test cases are specifications of the inputs to the test and the expected output from the system, the test results, plus a statement of what is being tested. Test data are inputs that have been devised to test a system. Test data can sometimes be generated automatically, but automatic test cases generations is impossible, as people who understand what the system is supposed to do must be involved to specify the expected test results. However, test execution can be automated. The expected results are automatically compared with the predicted results, so there is no need for a person to look for errors and anomalies in the test run. Typically, a commercial software system has to go through three stages of testing. 1. Development testing, where the system is tested during the development to discover bugs and defects. System designers and programmers are likely to be involved in testing process. Number 2. Release testing, where a separate testing team tests a complete version of the system before it is released to users. The aim of release testing is to check that the system meets the requirements of the system stakeholders. Number 3. User testing, where users or potential users of a system test the system in their own environment. For software products, the user may be an internal marketing group who decide if the software can be marketed, released, and sold. Acceptance testing is one type of user testing where the customer formally tests a system to decide if it should be accepted from the system supplier or if further development is required. In practice, the testing process usually involves a mixture of manual and automated testing. In manual testing, a tester runs the program with some test data and compares the results to their expectation. They note and report discrepancies to the program developers. In automated testing, the tests are encoded in a program that is run each time the system under development is to be tested. This is usually faster than the manual testing, especially when it involves regression testing, rerunning previous tests to check that changes to the program have not introduced in new bugs. The use of automated testing has increased considerably over the past few years. However, testing can never be completely automated, as automated testing can only check that a program does what it is supposed to do. It is practically impossible to use automated testing to test systems that depends on how things look, such as a graphical user interface, or the test that a program does not have unwanted side effects. Development testing. Development testing includes all testing activities that are carried out by the team developing the system. The tester of the software is usually the programmer who developed the software. Although this is not always the case, some development processes use programmer-tester pairs, where each programmer has an associated tester who develops, tests, and assists with the testing process. For critical systems, a more formal process may be used. with a separate testing group within the development team. They are responsible for developing, test, and maintaining detailed records of test results. During development, testing may be carried out at three levels of granularity. 1. Unit testing, where individual program units or object classes are tested. Unit testing should focus on testing the functionality of the objects or methods. Number 2. Component testing, where several individual units are integrated to create composite components. Component testing should focus on testing component interfaces. Number 3. System testing, where some or all of the components in a system are integrated and the system is tested as a whole. System testing should focus on testing component interactions. Development testing is primarily a defect testing process where the aim of testing is to discover bugs in the software. It is therefore usually interleaved with debugging, the process of locating problems with the code and changing the program to fix these problems. Unit testing. Unit testing is the process of testing program components such as methods or object classes. Individual functions or methods are the simplest type of component. Your test should be calls to these routines with different input parameters. When you are testing object classes, you should design your test to provide coverage of all of the features of the object. This means that you should test all operations associated with the object, set and check the value of all attributes associated with the object, put the object into all possible states. This means that you should simulate all events that cause a state change. The interface of this object is shown in the above figure. It has a single attribute which is its identifier. This is a constant that is set when the weather situation is installed. You therefore only need a test that checks if it has been properly set up. You need to define test cases for all the methods associated with the object such as report weather, report status, etc. Ideally, you should test methods in isolation, but in some cases, some test sequences are necessary. For example, to test the method that shuts down the weather station instrument's shutdown, you need to have executed the restart method. Generalization or inheritance makes object class testing more complicated. You can't simply test an operation in the class where it is defined and assume that it will work as expected in the subclass that inherit the operation. The operation that is inherited make assumptions about other operations and attributes. These may not be valid in some subclasses that inherit the operation. You therefore have to test the inherited operation in all of the context where it is used. To test the states of the weather station, you use a state model. Using this model, you can identify sequences of state transitions that have to be tested and define event sequences to force these transitions. In principle, you should test every possible state transition sequence, although in practice this may be too expensive. Examples of state sequences that should be tested in the weather station include shutdown, running, shutdown, configure, running, testing, transmitted, running, running, collecting, running, summarizing, transmitting, running. Whenever possible, you should automate unit testing. In automated unit testing, you make use of a test automation framework, such as JUnit, to write and run your program test. Unit testing framework provide generic test classes that you send to create specific test cases. They can then run all of the tests that you have implemented and report, often through some GUI, on the success or failure of the tests An entire test suite can often be run in a few seconds, so it is possible to execute all the tests every time you make a change to the program. An automated test has three parts. Number one, a setup part where you initialize the system with a test case, namely the inputs and expected outputs. Number two, a call part where you call the object or method to be tested. Number three, an assertion part where you compare the result of the call with the expected result. If the assertion evaluates to true, the test has been successful. If false, then it has failed. Sometimes the object that you are testing has dependencies on other objects that may not have been written or which slow down the testing process if they are used. For example, if your object calls a database, they may involve a slow setup process before it can be used. In these cases, you may decide to use mock object. Mock objects are objects with the same interface as the external objects being used that simulate its functionality. Therefore, a mock object simulate a database may have only a few data items that are organized in an array. They can therefore be accessed quickly without a overhead of calling a database and accessing disk. Similarly, mock objects can be used to simulate abnormal operation or rare events. For example, if your system is intended to take action at certain times of day, your mock object can simply return those times irrespective of the actual clock time. Choosing unit test cases. Testing is expensive and time consuming, so it is important that you choose effective unit test cases. Effectiveness in this case means two things. Number one, the test cases should show that when used as expected, the component that you are testing does what it is supposed to do. Number two, if there are defects in the component, these should be revealed by test cases. You should therefore write two kinds of test case. The first of these should reflect normal operation of a program and should show that the component works. For example, if you are testing a component that creates and initializes a new patient record, then your test case should show that the record exists in a database and that its fields have been set as specified. The other kind of test case should be based on testing experience of where common problems arise. It should use abnormal inputs to check that these are probably processed and do not crash the component. We discussed two possible strategies here that can be effective in helping you choose test cases. These are 1. Partition testing, where you identify groups of inputs that have common characteristics and should be processed in the same way. You should choose tests from within each of these groups. Number 2. Guideline based testing, where you use testing guidelines to choose test cases. These guidelines reflect previous experience of the kinds of error that programmers often make when developing components. The input data and output results of a program often fall into a number of different classes with common characteristics. Examples of these classes are positive numbers, negative numbers, and menu selections. Programmers normally behave in a comparable way for all members of a class. That is, if you test a program that does a computation and requires two positive numbers, then you would expect the program to behave in the same way for all positive numbers. Because of this equivalent behavior, these classes are sometimes called equivalence partition or domains. One systematic approach to test case design is based on identifying all input and output partitions for a system or component. Test cases are designed so that the inputs or outputs lies within these partitions. Partition testing can be used to design test cases for both systems and components. As shown in the figure, the large shaded ellipse on the left represents the set of all possible inputs to the program that is being tested. The smaller unshaded ellipses represent equivalence partitions. A program being tested should process all of the members of an input equivalence partitions in the same way. Output equivalence partitions are partitioned within which all of the outputs have something in common. Sometimes there is a 1:1 mapping between input and output equivalence partitions. However, this is not always the case. You may need to define a separate input equivalence partition where the only common characteristics of the inputs is that they generate outputs within the same output partition. The shaded area in the left ellipse represents outputs that are invalid. The shaded area in the right ellipse represents exceptions that may occur. Once you have identified a set of partitions, you choose test cases from each of these partitions. A good rule of thumb for test case selection is to choose test cases on the boundaries of the partitions, plus cases close to the midpoint of the partition. The reason for this is that designers and programmers tend to consider typical values of input when developing a system. You test these by choosing the midpoint of the partition. Boundary values are often atypical, such as 0 may behave different from other non-negative numbers, so are sometimes overlooked by developers. Program failure often occur when processing these atypical values. You identify partitions by using the program specification or use documentation and from experience where you predict the classes of input value that are likely to detect errors. For example, say a program specification states that the program accepts 4 to 8 inputs which are 5-digit integer greater than 10,000. You use this information to identify the input partition and possible test input values, as shown in the figure. When you use the specification of a system to identify equivalence partition, this is called black box testing. Here, you don't need any knowledge of how the system works. However, it may be helpful to supplement the black box testing with white box testing, where you look at the code of the program to find other possible tests. For example, your code may include exceptions to handle incorrect inputs. You can use this knowledge to identify exception partitions, different ranges where the same exception handling should be applied. Equivalence partitions is an effective approach to testing because it helps account for errors that programmers often make when processing inputs at the edges of partitions. You can also use testing guidelines to help choose test cases. Guidelines encapsulate knowledge of what kinds of test cases are effective for discovering errors. For example, when you are testing programs with sequences, arrays, or lists, guidelines that could help reveal defect knowledge. Number 1. Test software with sequences that have only a single value. Programmers naturally think of sequences as made up of several values, and sometimes they embed this assumption of their program. Consequently, if presented with a single value sequence, a program may not work properly. Number 2. Use different sequences of different sizes in different tests. This decreases the chances that a program with defects will accidentally produce a correct output because of some accidental characteristics of the input. Number 3. Derive tests so that the first, middle, and last elements of the sequence are accessed. This approach reveals problems at partition boundaries. Whitaker's book includes many examples of guidelines that can be used in test case design. Some of the most general guidelines that he suggests are: choose inputs that force the system to generate all error messages, design inputs that cause input buffers to overflow, repeat the same input or series of inputs numerous times, force invalid outputs to be generated, force computation results to be too large or too small. As you gain experience with testing, you can develop your own guideline about how to choose effective test cases. Component testing. Software components are often composite components that are made of several interacting objects. For example, in the weather station system, the reconfiguration component includes objects that deal with each aspect of the reconfiguration. You access that functionality of these objects through the defined component interface. Testing composite components should therefore focus on showing that the component interface behaves according to its specification. You can assume that unit tests on the individual objects within the component have been completed. As illustrated in the above figure, the idea of component interface testing assumes that components A, B, and C have been integrated to create a larger component or subsystem. The test cases are not applied to the individual component but rather to the interface of the composite component created by the combining these components. Interface errors in the composite component may not be detectable by testing the individual objects because these errors result from interacting between the objects in the component. There are different types of interface between program components and consequently different types of interface errors that can occur. Number 1. Parameter interfaces. These are interfaces in which data or sometimes function references are passed from one component to another. Methods in an object have a parameter interface. Shared memory interfaces. These are interfaces in which a block of memory is shared between components. Data is placed in the memory by one subsystem and retrieved from there by another subsystems. This type of interface is often used in embedded systems where sensors create data that is retrieved and processed by other system components. Number 3. Procedural interfaces. These are interfaces in which one component encapsulates a set of procedures that can be called by another component. Objects and reusable components have this form of interface. Number 4. Message passing interfaces. These are interfaces in which one component requests a service from another component by passing a message to it. A return message includes the results of executing the service. Some object-oriented systems have this form of interface, so do client-server system. Interface errors are one of the most common forms of errors in complex systems. These errors fall into three classes. Interface misuse. A calling component calls some other components and makes an error in the use of its interface. This type of error is common with parameter interface where parameters may be of the wrong type or be passed in the wrong order, or the wrong number of parameters may be passed. Interface misunderstanding. A calling component misunderstands the specification of the interface of the called component and makes assumptions about its behavior. The called component does not behave as expected, which then causes unexpected behavior in the calling component. For example, a binary search method may be called with a parameter that is an unordered array. The search would then fail. Timing errors. These occurs in real-time systems that use a shared memory or a message passing interface. The procedure of data and the consumer of data may operate at different speeds. Unless particular care is taken in the interface design, the consumer can access out-of-date information because the procedure of the information has not been updated the shared interface information. Testing for interface defects is difficult because some interface faults may only manifest themselves under unusual conditions. For example, say an object implements a queue as a fixed length data structure. A calling object may assume that the queue is implemented as an infinite data structure. may not check for queue overflow when an item is entered. This condition can only be detected during testing by designing test cases that force the queue to overflow and cause the overflow to corrupt the object behavior in some detectable way. A further problem may arise because of interactions between faults in different modules or objects. Faults in one object may only be detected when some other object behaves in an unexpected way. For example, an object may call another object to receive some service and assume that the response is correct. If the called service is faulty in some way, the returned value may be valid but incorrect. This is not immediately detected, but only becomes obvious when some later computation goes wrong. Some general guidelines for interface testings are: number 1. Examine the code to be tested and explicitly list each call to an external component. Design a set of tests in which the values of the parameters to the external components are at the extreme ends of their ranges. These extreme values are most likely to reveal interface inconsistencies. Number 2. Where points are passed across an interface, always test the interface with null pointer parameters. Number 3. Where a component is called through the procedural interface, design tests that deliberately cause the component to fail. Differing failure assumptions are one of the most common specification misunderstandings. Number 4. Use stress testing in message passing system. This means that you should design tests that generate many more messages that are likely to occur in practice. This is an effective way of revealing timing problems. Number 5. Where several components interact through shared memory, design tests that vary the order in which these components are activated. These tests may reveal implicit assumptions made by the programmer about the order in which the shared data is produced and consumed. Inspections and reviews can sometimes be more cost effective than testing for discovering interface errors. Inspections can concentrate on component interfaces and questions about the assumed interface behavior asked during the inspection process. A strongly typed language such as Java allows many interface errors to be trapped by the compiler. Static Analyzer can detect a wide range of interface errors. System testing. System testing during development involves integrating components to create a version of the system and then testing the integrated system. System testing checks that components are compatible, interact correctly, and transfer the right data at the right time across their interfaces. It is obviously overlaps with component testing, but there are two important differences. Number 1, during system testing, reusable components that have been separately developed and off-the-shelf systems may be integrated with newly developed components and complete system is then tested. Number 2, components developed by different team members or groups may be integrated at this stage. System testing is a collective rather than an individual process. In some companies, system testing may involve a separate testing team with no involvement from designers and programmers. When you integrate components to create a system, you get emergent behavior. This means that some elements of system functionality only become obvious when you put the components together. This may be planned emergent behavior, which has to be tested. For example, you may integrate an authentication component with a component that updates information. You then have a system feature that restricts information updating to authorized users. Sometimes, however, the emergent behavior is unplanned and unwanted. You have to develop tests that check that the system is only doing what it is supposed to do. Therefore, system testing should focus on testing the integration between the components and the objects that make up a system. You may have also test reusable components and systems to check that they work as expected when they are integrated with new components. This interaction testing should discover those components bugs that are only revealed when a component is used by other components in the system. Interaction testing also helps find misunderstanding made by component developer about other components in the system. Because of its focus on interaction, use case-based testing in an effective approach to system testing. Typically, each use case is implemented by several components or objects in the system. Testing the use case forces these interactions to occur. If you have developed a sequence diagram to model the use case implementation, you can see the objects or components that are involved in the interaction. To illustrate this, we use an example from the Wilderness Weather Station system where the weather station is asked to support summarized weather data to a remote computer. As shown in the figure, the sequence of the operations in the weather station when it responds to a request to collect data for the mapping system. You can use this diagram to identify operations that will be attested and to help design the test cases to execute the test. Therefore, issuing a request for a report will result in the execution of the following thread of methods: setcoms request weather station report weather, comsling get summary weather data summarize. The sequence diagram helps you to design the specific test cases that you need, as it shows that what input are required and what outputs are created. Number 1. An input of a request for a report should have an associated acknowledgement. A report should ultimately be returned from the request. During testing, you should create summarized data that can be used to check that the report is correctly organized. Number 2. An input request for a report to weather station results in a summarized report being generated. You can test this in isolation by creating raw data corresponding to the summary that you have prepared for the test of SATCOMs and checking that the weather station object correctly produces this summary. This raw data is also used to test the weather data object. Of course, we have simplified the sequence diagram as shown in the figure so that it does not show exceptions. A complete use case scenario test must also take these input account and ensure that objects correctly handle exceptions. For most systems, it is difficult to know how much system testing is essential and when you should to stop testing. Exhaustive testing, where every possible program execute sequence is tested, is impossible. Testing, therefore, has to be based on a subset of possible test cases. Ideally, software companies should have policies for choosing this subset. These policies might be based on general testing policies, such as a policy that all program statements should be executed at least once. Alternatively, they may be based on experience of system usage and focus on testing the features of operational system. For example, all system functions that are accessed through menus should be tested. Combinations of functions, such as text formatting that are accessed through the same menu, must be tested. Where user input is provided, all functions must be tested with both correct and incorrect inputs. It is clear from experience with major software products such as word processors or spreadsheets that similar guidelines are normally used during product testing. When features of the software are used in isolation, they normally work. Problems arises, as Whitaker 2002 explains, when combinations of less commonly used features have not been tested together. He gives the example of how in a commonly used word processor using footnotes with a multi-column layout causes incorrect layout of text. Automated system testing is usually more difficult than automated unit or component testing. Automated unit testing relies on predicting the output, then encoding these predictions in a program. The prediction is then compared with the result. However, the point of implementing a system may be to generate outputs that are large or cannot be easily predicted. You may be able to examine an output and check its credibility without necessarily being able to create it in advance. Test-driven development. Test-driven development is an approach to program development in which you interleave testing and code development. Essentially, you develop the code incrementally along with a test for the increment. You don't move on the next increment until the code that you have developed passes its test. Test-driven development was introduced as part of agile methods such as extreme programming. However, it can also be used in planning-driven development processes. The fundamental TDD process is shown in the following figure. The steps in the process are as follows. Number 1. You start by identifying the increment of functionality that is required. This should normally be small and implementable in a few lines of code. Number 2. You write a test for this functionality and implement this as an automated test. This means that the test can be executed and will report whether or not it has passed or failed. Number 3. You then run the test along with all other tests that have been implemented. Initially, you have not implemented the functionality, so the new test will fail. This is deliberate as it shows that the test adds something to the test set. Number 4. You then implement the functionality and rerun the test. This may involve refactoring existing code to improve it and add new code to what's already there. Number 5. Once all tests run successfully, you move on implementing the next chunk of functionality. An automated testing environment such as JUnit environment that supports Java program testing is essential for TDD. As the code is developed in very small increments, you have to be able to run every test each time that you add functionality or refactor the program. Therefore, the tests are embedded in a separate program that runs the test and invokes the system that is being tested. Using this approach, it is possible to run hundreds of separate tests in a few seconds. A strong argument for test-driven development is that it helps programmers clarify their ideas of what a code segment is actually supposed to do. To write a test, you need to understand what is intended, as this understanding makes it easier to write the required code. Of course, if you have incomplete knowledge or understanding, then test-driven development would not help. If you don't know enough to write the test, you would not develop the required code. For example, if your computation involves division, you should check that you are not dividing the numbers by 0. If you forget to write a test for this, then the code to chunk will never be included in the program. As well as better problem understanding, our benefits to test-driven development are: Number 1. Code coverage. In principle, every code segment that you write should have at least one associate test. Therefore, you can be confident that all of the code in this system has actually been executed. Code is tested as it is written, so defects are discovered early in the development process. Number 2. Regression testing. A test suite is developed incrementally as a program is developed. You can always run a regression test to check that changes to the program have not introduced new bugs. Number 3. Simplified debugging. When a test fails, it should be obvious where the problem lies. The newly written code needs to be checked and modified. You do not need to use debugging tools to locate the problem. Reports of the use of test-driven development suggest that it is hardly ever necessary to use an automated debugging in test-driven development. Number 4. System documentation. The tests themselves act as a form of documentation that describe what the code should be doing. Reading the tests can make it easier to understand the code. One of the most important benefits of test-driven development is that it reduces the cost of regression testing. Regression testing involves running tests that have successfully executed after changes have been made to a system. The regression test checks that these changes have not introduced new bugs into the system and that the new code interacts as expected with the existing code. Regression testing is very expensive and often impractical when a system is manually tested. As the cost in time and effort are very high, in such situations you have to try and choose the most relevant test, rerun, and it is easy to miss important tests. However, automated testing, which is fundamental to test-first development, dramatically reduces the cost of regression testing. Existing tests may be rerun quickly and cheaply. After making a change to a system in test-first development, all existing tests must run successfully before any further functionality is added. As a programmer, you can be confident that the new functionality that you have added has not caused or revealed problems with existing code. Test-driven development is the most used in new software development where the functionality is either implemented in new code or by using well-tested standard libraries. If you are reusing large code components or legacy systems, then you need to write tests for these systems as a whole. Test-driven development may also be ineffective with multi-threaded systems. The different threads may be interleaved at different times in different test runs and so may produce different results. If you use test-driven development, you still need a system testing process to validate the system. That is to check that it meets the requirements of all the system stakeholders. System testing also tests performance, reliability, and checks that the system does not do things that it should not do, such as produce unwanted outputs, etc. Andrea in 2007 suggests how testing tool can be extended to integrate some aspects of system testing with TDD. Test-driven development has proved to be a successful approach for small and medium-sized projects. Generally, programmers who have adopted this approach are happy with it and find it a more productive way to develop software. In some trials, it has been shown to lead the improved code quality. In others, the results have been inconclusive. However, there is no evidence that TDD leads to poorer quality code. Release testing. Release testing is the process of testing a particular release of a system that is intended for use outside of the development team. Normally, the system release is for customers and users. In a complex project, however, the release could be for another team that are developing related systems. For software products, the release could be for product management who then prepare it for sale. There are two important distinctions between release testing and system testing during the development process. Number 1. A separate team that has not been involved in the system development should be responsible for release testing. Number 2. System testing by the development team should focus on discovering bugs in the system. The objective of release testing is to check that the system meets its requirement and is good enough for external use. The primary goal of the release testing process is to convince the supplier of the system that it is good enough for use. If so, it can be released as a product or delivered to the customer. Release testing therefore has to show that the system delivers its specified functionality, performance, and dependability, and that it does not fail during normal use. It should take into account all of the system requirements, not just the requirements of the end users of the system. Release testing is usually a black box testing process where tests are derived from the system specification. The system is treated as a black box whose behavior can only be determined by studying its inputs and the related outputs. Another name for this is functional testing, so called because the tester is only concerned with functionality and not the implementation of the software. Requirement-based testing. A general principle of good requirements engineering practice is that requirements should be testable. That is, the requirement should be written so that a test can be designed for the requirement. A tester can then check that the requirement has been satisfied. Requirements-based testing, therefore, is a systematic approach to test case design where you consider each requirement and derive a set of tests for it. Requirements-based testing is validation rather than defect testing. You are trying to demonstrate that the system has probably implemented its requirements. For example, consider related requirements for the MHC, PMS, which are concerned with checking for drug allergies. If a patient is known to be allergic to any particular medicine, then prescription of that medication shall result in a warning message being issued to the system user. If a prescriber chooses to ignore an allergy warning, they shall provide a reason why this has been ignored. To check if these requirements have been satisfied, you may need to develop several related tests. Number 1. Set up a patient record with no known allergies. Prescribe medication for allergies that are known to exist. Check that a warning message is not issued by the system. Number 2. Set up a patient record with a non-allergy. Prescribe the medication to that the patient is allergic to and check that the warning is issued by the system. Number 3. Set up a patient record in which allergies to 2 or more drugs are recorded. Prescribe both of these drugs separately and check that the correct warning for each drug is issued. Number 4. Prescribe 2 drugs that the patient is allergic to. Check that 2 warnings are correctly issued. Number 5. Prescribe a drug that issues a warning and overrule the warning. Check that the system requires the user to provide information explaining why the warning was overruled. You can see from this that testing is required does not mean just writing a single test. You normally have to write several tests to ensure that you have coverage of the requirement. You should also maintain traceability records of your requirements-based testing, which link the test to the specific requirements that are being tested. Scenario testing. Scenario testing is an approach to release testing where you devise typical scenarios of use and use these to develop test cases for the system. A scenario is a story that describes one way in which the system might be used. Scenarios should be realistic and real system users should be able to relate to them. If you have used scenarios as part of the requirement engineering process, then you may have been able to reuse these as testing scenarios. In a short paper on scenario testing, Kenner suggests that scenario tests should be narrative story that is credible and fairly complex. It should motivate stakeholders, that is, they should relate the scenario and believe that it is important that the system passes the test. He also suggests that it should be easy to evaluate. If there are problems with the system, then the release testing team should recognize them. As an example of a possible scenario from the MHC PMS describes one way that the system may be used on a home visit. It tests a number of features of the MHC PMS. Number 1. Authentication by logging on to the system. Number 2. Downloading and uploading of specified patient records to a laptop. Number 3. Home visit scheduling. Number 4. Encryption and decryption of patient records on a mobile device. Number 5. Record retrieval and modification. Number 6. Links with the drug database that maintains side effects information. Number 7. The system for call prompting. If you are a release tester, you run through this scenario, playing the role of Kate and observe how the system behaves in response to different inputs. As Kate, you make deliberate mistakes such as inputting the wrong key phrase to decode records. This checks the response of the system to errors. You should carefully note any problems that arise, including performance problem. If a system is too slow, this will change the way that it is used. For example, if it takes too long to encrypt a record, then users who are short of time may skip this stage. If they then lose their laptop, an authorized person could then view the patient records. When you use a scenario-based approach, you are normally testing several requirements within the same scenario. Therefore, as well as checking individual requirements, you are also checking that combinations of requirements do not cause problems. Performance testing. Once a system has been completely integrated, it is possible to test for emergent properties such as performance and reliability. Performance tests have to be designed to ensure that the system can process its intended load. This usually involves running a series of tests where you increase the load until the system performance becomes unacceptable. As with other types of testing, performance testing is concerned both with demonstrating that the system meets its requirement and discovering problems that defects in the system. To test whether performance requirements are being achieved, you may have to construct an operational profile. An operational profile is a set of tests that reflect the actual mix of work that will handled by the system. Therefore, if 90% of the transactions in a system are of type A, 5% of type B, and the remainder of type C, D, and E, then you have to design the operational profile so that the vast majority of tests are of type A. Otherwise, you will not get an accurate test of the operational performance of the system. This approach, of course, is not necessarily the best approach for defect testing. Experience has shown that an effective way to describe defects is to design tests around the limits of the system. In performance testing, this means stressing the system by making demands that are outside the design limits of the software. This is known as stress testing. For example, say you are testing a transaction processing system that is designed to process up to 300 transactions per second. You start by testing this system with fewer than 300 transactions per second. You then gradually increase the load on the system beyond 300 transactions per second until it is well beyond the maximum design load of the system and the system fails. This type of testing has two functions. Number 1, it tests the failure behavior of the system. Circumstances may arise through an unexpected combination of events where the load placed on the system exceeds the maximum anticipated load. In these circumstances, it is important that the system failure should not cause data corruption or unexpected loss of user services. Stress testing checks that overloading the system causes it to fail soft rather than collapse under its load. Number 2, it stresses the system and may cause defects to come to light that would not normally be discovered, although it can be urged that these defects are unlikely to cause system failures in normal usage. There may be unusual combinations of normal circumstances that the stress testing replicates. Stress testing is particularly relevant to distributed systems based on a network of processors. These systems often exhibit several degradations when they are heavily loaded. The network becomes swamped with coordination data that the different processes must exchange. The processes become slower, and slower as they wait for the required data from other processes. Stress testing helps you discover when the degradation begins so that you can add checks to the system to reject transactions beyond this point. User testing. User or customer testing is a stage in the testing process in which users or customers provide input and device on system testing. This may involve formally testing a system that has been commissioned from an external supplier, or could be an informal process where users experiment with a new software product to see if they like it or that it does what they need. User testing is essential, even when comprehensive system and release testing have been carried out. The reason for this is that influences from the user's working environment have a major effect on the reliability, performance, usability, and robustness of a system. It is practically impossible for a system developer to replicate the system's working environment, as tests in the developer's environment are inevitable artificial. For example, a system that is intended for use in a hospital is used in a clinical environment where other things are going on, such as patient emergencies, conversations with relatives, etc. These all affects the use of a system, but developers cannot include them in their testing environment. In practice, there are three different types of user testing. Number one, alpha testing, where users of the software work with the development team to test the software at the developer's site. Number two, beta testing, where a release of the software is made available to users to allow them to experiment and to raise problems that they discover with the system developers. Number three, acceptance testing, where customers test a system to decide whether or not it is ready to be accepted from the system developers and deployed in the customer environment. In alpha testing, users and developers work together to test a system as it is being developed. This means that the users can identify problems and issues that are not readily apparent to the development testing team. Developers can only really work from the requirements, but these often do not reflect other factors that affect the practical use of the software. Users can therefore provide information about practice that helps with the design of more realistic tests. Alpha testing is often used when developing software products that are sold as shrink-wrapped systems. Users of these products may be willing to get involved in the alpha testing process because this gives them early information about new system features that they can exploit. It also reduces the risk that unanticipated changes to the software will have disruptive effect on their business. However, alpha testing may also be used when custom software is being developed. Agile methods such as XP advocate user involvement in the development process and that user should play a key role in designing tests for the system. Beta testing takes place when an early, sometimes unfinished, release of software system is made available to customers and users for evaluation. Beta testers may be a selected group of customers who are early adopters of the system. Alternatively, the software may be made publicly available for use by anyone who is interested in it. Beta testing is mostly used for software products that are used many different environments as opposed to custom systems which are generally used in a defined environment. It is impossible for product developers to know and replicate all the environments in which the software will be used. Beta testing is therefore essential to discover interaction problems between the software and features of the environment where it is used. Beta testing is also a form of marketing. Customers learn about their system and what it can do for them. Acceptance testing is an inherent part of custom systems development. It takes place after release testing. It involves a customer formally testing a system to decide whether or not it should be accepted from the system developer. Acceptance implies that payment should be made for the system. There are 6 stages in the acceptance testing process as shown in the figure. They are: number 1, define acceptance criteria. This stage should ideally take place early in the process before the contract for the system is signed. The acceptance criteria should be part of the system contract and be agreed between the customer and the developer. In practice, however, it can be difficult to define criteria so early in the process. Detailed requirements may not be available and there may be significant requirement changes during the development process. Number 2, plan acceptance testing. This involves deciding on the resources, time, and budget for acceptance testing and establishing a testing schedule. The acceptance test plan should also discuss the required coverage of the requirements and the order in which system features are tested. It should define risks to the testing process, such as system crashes and inadequate performance, and discuss how these risks can be mitigated. Number 3, derive acceptance tests. Once acceptance criteria have been established, tests have to be designed to check whether or not a system is acceptable. Acceptance tests should aim to test both the functional and non-functional characteristics, such as performance of the system. They should ideally provide complete coverage of the system requirement. In practice, it is difficult to establish completely objective acceptance criteria. There is often scope of argument about whether or not a test shows that a criterion has definitely been met. Number 4, run acceptance tests. The agreed acceptance tests are executed on the system. Ideally, this should take place in actual environment where the system will be used, but this may be disruptive and impractical. Therefore, a user testing environment may have to be set up to run these tests. It is difficult to automate this process as part of the acceptance tests and may involve testing the interaction between end users and the system. Some training of the end users may be required. Negotiate test results. It is very unlikely that all of the defined acceptance tests will pass and that there will be no problems with the system. If this is the case, then acceptance testing is complete and the system can be handed over. More commonly, some problems will be discovered. In such cases, the developer and the customer have to negotiate to decide if the system is good enough to be put into this use. They must also agree on the developer's response to identify problem. Number 6, reject accept systems. This stage involves a meeting between the developers and the customer to decide on whether or not the system should be accepted. If the system is not good enough for use, then further development is required to fix the identified problems. Once complete, the acceptance testing phase is repeated. In agile methods, such as XP, acceptance testing has a rather different meaning in principle. It shares the notation that users should decide whether or not the system is acceptable. However, in XP, the user is part of the development team, such as he or she is an alpha tester, and provides the system requirement in the terms of user stories. He or she is also responsible for defining the tests, which decide whether or not the developed software supports the user story. The tests are automated and developed does not proceed until the story acceptance tests have passed. There is, therefore, no separate acceptance testing activity. One problem with user involvement is ensuring that the user who is embedded in the development team is a typical user with general knowledge of how the system will be used. It can be difficult to find such a user, and so the acceptance tests may actually not be a true reflection of practice. Furthermore, the requirement for automated testing several limits the flexibility of testing interactive systems. For such systems, acceptance testing may require groups of end users to use the system as if it was part of their everyday work. You might think that acceptance testing is clear-cut contractual issue. If a system does not pass its acceptance test, then it should not be accepted and payment should not be made. However, the reality is more complex. Customers want to use the software as soon as they can because of the benefits of its immediate deployment. They may have bought new hardware, trained staff, and changed their processes. They may be willing to accept the software irrespective of problems because the cost of not using the software are greater than the cost of working around the problems. Therefore, the outcome of negotiations may be conditional acceptance of the system. The customer may accept the system so that the deployment can begin. The system provider agrees to repair urgent problems and deliver a new version to the customer as quickly as possible. Key points. Testing can only show the presence of errors in a program. It cannot demonstrate that there are no remaining faults. Development testing is the responsibility of the software development team. A separate team should be responsible for testing a system before it is released to customers. In the user testing process, customers or system users provide test data and check that tests are successful. Development testing includes unit testing, in which you test individual objects or methods. Component testing, in which you test related groups of objects, and system testing, in which you test partial or complete systems. When testing software, you should try to break the software by using experience and guidelines to choose type of test cases that have been effective in discovering defects in other systems. Wherever possible, you should write automated tests. The tests are embedded in a program that can be run every time a change is made to a system. Test-first development is an approach to development where tests are written before the code to be tested. Small code changes are made and the code is refactored until all tests execute successfully. Scenario testing is useful because it replicates the practical use of the system. It involves inventing a typical usage scenario and using this to derive test cases. Acceptance testing is a user testing process where the aim is to decide if the software is good enough to be deployed and used in its operational environment.